Hi, everybody. Hope everybody's doing well. There's been a lot of things happening this semester, and I really feel sorry for everybody, including not me. I got it good. We have electricity. No one's sick in our house, and I hope you all can say the same thing. And I just hope you all have a good end of the semester. It's been rough, but we're finishing up this week, our final week of lectures. And I did change some deadlines, and hopefully everybody has seen those changes. I'll mention a few of them right now. The final two homeworks, assignment 6 and 7, are going to be due on Friday, April 24th. And it'll cover electrochemistry, separations, and chromatography. Exam 3 will be on Friday, the 24th also, and it'll cover our topics in Chapter 10, EDTA titrations, Chapter 11, UV-vis absorbance, topics in electrochem, and our separations in chromatography, where we end at the beginning of today. It'll be open from 1 p. until 2 p. on Friday, April 24th. Once you start it, you can't stop it. So my suggestion when you take the exam, be prepared. If you want to use your textbook, your notebooks, I'm okay with it. I'm considering this open book. Use whatever resources that you want. You can have any equations that you want from your textbook right in front of you, because chromatography, as we're going to show today, involves a lot of times using the right equation and plugging numbers in and understanding what you're doing. And also units, making sure that your units are correct. And we'll be emphasizing that today. The final exam is set for a week later. It's going to be on Friday, May 1st, and it's cumulative. It'll cover all the material plus the final lectures that we're going to do, and I'll be discussing that today. It's going to start at 10:30 and end at 12:30. You'll have a 2-hour window, and you can't stop or restart, similar to all of our other exams. I have a list of textbook problems to go through to help you succeed at the end of this semester. Today, our lecture is going to be finishing up topics at the very beginning that may be covered on our third exam. And these are a summary of how we use equations. And I'm actually going to do a sample problem. And I'm hoping that I get more input from you people out there with problems that you're having. Remember, Wednesday, if you guys send me some questions, I will go over them. But remember, these questions that you ask me, find questions in your textbook if you're having a problem on the Sapling homework that are very similar. Don't just say, Dr. Patton, do number 4 from Sapling. I'll give you advice, but I won't solve it for you. I would rather get problems that I can solve in the YouTube video format, and that way you get more out of it when you see how I solve the problem rather than just giving you tips. So we'll go over equations today that we use. We're going to also discuss a lot about resolution. Resolution is very important when we try to separate components from a complex mixture. And that's an important topic that we'll finish today. And that'll be the final topic on exam 3. And then we're going to start into some final exam material. In this lecture, I will introduce the Van Deemter equation, and we'll discuss what the Van Deemter equation is. And in many cases, we don't solve it, but we look at the Van Deemter equation to help us understand parameters that we control when we conduct a separation experiment using a chromatographic method. In our next lecture, we're actually going to discuss a little bit about the similarities and differences between gas chromatography and liquid chromatography. I will be using a few of those today when we discuss some of our dealings with resolution, but I will emphasize these more when we compare the two methods. And for those lectures, I'm actually going to take the video into the laboratory and look at the instrument. You'll get more out of the differences and similarities when you see the instruments that you use for these types of experiments. And our final topic that we'll finish up with at the very end of the lectures on Friday is quantitative applications, how we make up a calibration plot, how we use peak area to help us understand a little bit about the relationship between how much of a substance is in a sample and the chromatograms that we're working with. So in our lab section, my lab section, you've had some experience with those, and I will go over it in more detail for everybody in the lecture course. So today, if you're looking at the slides that I have prepared for you, I do have a table on the slides that gives you a nice summary of the equations that we use to solve problems dealing with a chromatographic separation strategy. I actually added one more on here, and that's how we define resolution when we're given peak width at half height. That's really common. Peak width at half height is a situation in which we have a chromatogram. And last week we were discussing more about peak width at the base. Sometimes that's hard to measure. An easier parameter oftentimes is the peak width at half max. And that's what we use in a lot of our applications, especially when we're defining what our resolution is. An equation that we have for using this peak width at half height is that resolution, and this again is using some geometry, is equal to 0.589 times the differences in the retention times between two species divided by their peak width at half max. And that's listed here as W with a small subscript 1/2. So we're going to look at an example that someone actually did ask a question similar to this. This is real similar. They actually asked a question from the homework, and I said, well, I'll make up a question that's similar to the homework. And we're going to look at some experimental data that they're giving us, and we're going to solve some problems. So if you're reading through this problem, this is a review example, and in this example, they tell us that we have a column, and the column has a length of 18.1 centimeters. And they also give us some data about two species that are coming off of our column. So what we're imagining is that we're collecting a chromatogram of two species. We have A and we have B. So we'll just assume that these are what A and B may look like. A has a retention time of 10 minutes. And a little bit later, here comes B. It comes out at 11.24 minutes. So essentially what our question's dealing with and wants to know is we want to calculate what the width at half max is. That's this value for each of these two peaks. And we give you their retention time, and then we give you their plate height. Remember, plate height is H. That's the HETP that we sometimes see. That's the height equivalency of a theoretical plate. It tells us a little bit about the efficiency of our separation. So I'm going to go through this. I have some data written up here for the first one, and then I'll go through it for our second one. So the strategy that I'm going to use from the data that's given to me, what I'm going to do is I'm going to, first of all, I'm going to remember a formula that I have on the equation sheet. Again, you're on the exam. This will be in front of you. And we're trying to figure out what our width at half max is. And we have an equation that we went through in our last lecture, and we can figure out that the number of theoretical plates is equal to 5.55 times the square of the retention time divided by the width at half max. We're going to use that. We're going to use that information. You might say, well, Dr. Patton, where are we going to get N at? We can figure out what N is. N, remember, is defined as the length of our column divided by our HETP, our height equivalence of a theoretical plate. And I have both of those pieces of information in the question. Here's our L. L is 18.1 centimeters. I have that written right here. And here's our HETP. H is what we use oftentimes. It's the height equivalence of a theoretical plate. The number of plates is the length of the column divided by the height of each of those little plates that are inside that column. Issue here, once again, a lot of problems, units. Make sure your units are compatible. Notice 18.1 centimeters is the length of the column. The plate height, 8.24 micrometer. We have to convert our micrometer to centimeters, and we simply do that by multiplying 8.24 times 10 to the negative fourth. And that's our relationship between a micrometer and a centimeter. So we take the 18.1 divided by 8.24 times 10 to the negative fourth centimeters, and that tells us the number of theoretical plates that particular peak has. So this peak has an n value, and I'm going to give it a little subscript A, just so I know that we're talking about our first peak, A in this case. A has 21,966 plates. And I'm going to rearrange this equation. And this just requires doing some algebra and keeping variables separated and going through all that fun stuff that you probably learned in 7th grade, 6th grade, some of you. If we rearrange this equation and solve for W half, that's our width at half height, which we wanted. I show you the formula here, how I rearranged it, and I get some numbers in here. I get the 5.55 divided by 21,966, and it's multiplied by TR, and that's squared. I kept that squared. The retention time is 10 minutes, and I take the square root of that to get rid of the square from the W of 1/2. Because remember, the square, it's the ratio of those two. And that gives me the width at half height, half max, and I have it in minutes, 0.1589 minutes. And my question is, what is it in seconds? So I'm asking for it in seconds. I convert it to seconds by multiplying by 60 seconds for each minute, and I get a width at half max of that peak, 9.54 seconds. And I have it written up here in this table just to use it. So there's A, has a retention time of 10 minutes. The HETP, the height equivalency of a plate, 8.24 micrometers, which tells us a little bit something about the width. And we use that information to tell us what the width at half max is in seconds. I'm going to keep it in minutes too, just in case, because I'm going to use that later. So that was for A. We could do the same thing for B. We could solve it the exact same way for B. And let's set it up for B. And so B. We would use the same formula, but we're going to make a few changes. Now, the thing that's different about B, I'll use red so we can distinguish it. Here's B. The column has the same length. It's still 18.1 centimeters, but notice B has a larger H. That means it's not quite as efficient. A small plate height means we got better efficiency. A larger plate height indicates that we got poorer efficiency. So B has a slightly less efficient H value. We're going to put that into our denominator. And we would calculate the N for B, 17,000. 885. Okay, let's make sure these numbers make sense. The plate height for A is shorter. A had a greater number of theoretical plates. We calculated A. We'll just keep that here. A was 21,966. B, well, the plate height is larger, so there's going to be a less number of theoretical plates, and we get slightly less efficient separation for B. And we'll just keep this here for N. That's our number of theoretical plates. For B, 17,885. And we would plug this into this equation, 17,885. And we make two changes over here. First of all, our N value is different. And the retention time is different. For B, B is coming out a little bit later from our column. And this does make sense. Remember, when peaks come out later, they normally get broader. And one of the reasons for that is because we have more time for those solute particles to diffuse, both forward and backward. So the retention time for B is 11.24 minutes. And we would go through this, and we would find that for B, the peak width at half height in minute is 0.198. And it has a peak width at half height, half max in seconds, is 11.88 seconds. So let's put this information in for our B value now. It's over here. Here's B. The width at half max is 11.88 seconds, or 0.198 minutes. I probably should have retained one extra significant figure, but I didn't write it down in my notes. I'm really sorry. So, if you want to retain a little bit more data, always do so. It's probably important. So that was the first part of our question. I wrote this up here for a reason, because we're also going to calculate the resolution of the two peaks. Remember, we said normally we have two peaks, and that's the goal of almost any chromatographic experiment, is to get good resolution separation between any of the species that we're trying to purify or isolate on their own. And normally we want a resolution of greater than 1.5 to tell us that, hey, we did a good job of what we were attempting to do. So let's calculate our resolution. And we're going to pay close attention once again to our units. It's real important. And we're going to use this formula up here. Resolution. Sometimes you'll see a resolution just with a little s on it. Sometimes you do. Sometimes you don't. So I'm going to put it there just in case you see it. Resolution, and I'll stay with the red pen. I don't want to mess people's eyes up too much, is equal to 0.589 times the difference in our resolution, our retention times. So let's look at our two retention times. And when we calculate delta TR, it's the one that came out at a later time minus the guy that came out at the earlier time. So the differences in our TR, our retention time, is 11.24 minutes minus 10 minutes. And we're going to divide that by our width at half max, the average of the two. So the average is, we're just going to simply add the two together. And since we're adding two of them, divide by 2, that's the average. So this is where we have to make a decision. And once again, use our units, the proper units. The resolution is going to be a unitless number. So since these are in minutes, we're going to need our width at half max. I'm going to use the minute ones. just to make my life easier. I could have converted these to seconds, but I decided to use the minutes instead of the seconds for the peak width at half max. Any questions, send me an email. I'll shoot it back to you and answer the best I can. So let's make sure we have this all bracketed off so we know what we're doing. It's the addition of these two. Divided by 2. So it's the ratio of this divided by the ratio of those two added divided by 2. And I get a resolution 4.1. We're doing a pretty good job. If 1.5 was our goal, we have pretty good separation of the two components, and that's one of our main goals of any type of chromatographic strategy, good resolution. And that's a topic that we're going to finish up today. Resolution, a major goal when we're conducting a separation experiment using chromatography. Let's look at what we mean by resolution, and let's compare a chromatogram that has good resolution versus one that has bad resolution, so we can visualize what's going on here. Again, I have these listed on today's PowerPoint, so you might want to refer to these as we go through this slide present or the YouTube video. So here's my notes. I'm going to go over these. And I'm going to look at two chromatograms. And I'm going to look at one that has good resolution and one that has bad resolution. So again, I am not the best artist. I'll do my best. We have a chromatogram, and what we're using in these chromatograms is UV-vis absorbance as a detector to tell us a little bit something about how much of each component is in these different samples. Because peak area is related to concentration, such as we're going to show a little bit later when we get into quantitative applications of chromatography. So we have our time. We have time on this scale. And we're going to assume this is in minutes. This is time in minutes. And we have our detector response. And we're using absorbance. Remember, we learned about absorbance. Absorbance is a good detector to use in a lot of our chromatography experiments for certain reasons. So we'll discuss. So let's look at our first chromatogram. There's one guy, and there's another guy, and there's another guy, and then we get another guy. And then we get another guy. So we have 5 components. I mean, we can separate mixtures that have a lot of stuff in it. This one has 3 guys in it. 5 guys. I'm sorry, 5 guys. So we have five substances in here. And we're going to look at our time scale. Down here is 0.9 minutes. What's this? 0.8. So 0.8. At 0.8 minutes, we're done. We're getting our last peak out. How many guys do we have? We have 1, 2, 3, 4, 5. This would be an example of a chromatogram that we have some information also about how the experiment was conducted. Now, one factor that we can influence is temperature. This was conducted at 100 degrees Celsius. And it also gives you 5 milliliters per minute. What's that? What is 5 milliliters per minute? 5 milliliters per minute is equal to our flow rate. Flow rate. This is a volume flow rate. Flow rate. It tells us how fast our mobile phase is moving. That's what that rate is telling us. Because remember, in chromatography, We have a mobile phase that's moving and a stationary phase that's stationary. It's not moving. And what we're trying to do is encourage our solute to spend more time either in the stationary or mobile phase, while another component spends a different time in those two phases. And we encourage them to separate as they move to the end of the column. And we use a detector to tell us which one is which. Okay. We have another chromatogram here. Let's go through that one. Because the problem with this, can we see the problem? Hopefully we can. 3, 4, and 5. Good resolution. Those look pretty good. They're all resolved. They're all separate from each other. Problem we're having, component 1 and 2, they're not separated. Notice that the signal, in other words, the peak doesn't come back to the baseline, and we get what we don't get baseline resolution. And in this example, I would say that that's a bad job for sample 1 and 2. We can improve. We should strive to improve our strategy for separating them, because those two aren't coming off in separate peaks. So we can make some changes. And once again, we have our absorbance on this scale, and we have time on this scale, still in minutes. And we're going to get our peaks. So notice in this case, let's number them and let's put our time on here. That's important. We got 1, 2, 3, 4, 5. I think 3 is a little higher in the graph that's actually in the PowerPoint. Let's write down our conditions for this particular experiment. Okay, we made some changes to the conditions that we're conducting our experiment. When we made some changes, we should recognize that, okay, 1 and 2 are now separate. They have baseline resolution. Notice the signal for 1 goes up, it comes back to the baseline before we get a signal for our second sample that's coming off the column. That's good. We got good resolution. We have 5 peaks now that are coming off. 5 is getting a little broader. That's one bad thing. But probably the thing that's going to hurt your boss if you're working in grad school the most is that this experiment took less than a minute. That's 0.8 minutes. It's pretty quick. This one took 12 minutes. We've more than increased our analysis time by a factor of 10. So if we got to do 20 samples and each of them are taking 10 minutes, that's going to take some time. Whereas if we had these situations, we're going to be able to do those 10 samples a lot quicker. So this is giving us better resolution at a cost, though. The cost is more analysis time. This is often called the general elution problem. We might get poor separation, but we might have to make some changes in what we're doing to encourage that separation, and that's going to cost us time. So we have to balance things. We have to decide when we're conducting our experiment, what do we want? Do we want it to be done quickly? Are we working in an industry where time's of the essence? Or do we want better resolution? Notice some factors that I changed here. We've changed the temperature. That's one factor that we can do in an experiment. We can change our temperature to encourage a separation. And we'll be discussing that in a few minutes. And we've also changed our flow rate for our mobile phase. Notice the slower flow rate cost us more time. So that might be something you would recognize right away. slower flow rate costs more time, but it looks like for this example, we got better resolution. So those are two factors that we can encourage to create better resolution: temperature, flow rate. And there's several others. There's several other types of parameters that we can change to encourage our resolution. I have another equation to define resolution. Again, a pretty complex equation, but it's the factors or the parameters that make up the equation that I think are really important. Because what I want to show in this equation is that there are three overlying factors that we can encourage to improve our resolution. So again, this is on today's PowerPoint slide. If you're looking at it, we're going to redefine our resolution equation. Again, these are all available to you. You should be able to find this, but I think this equation is really useful for understanding about the parameters that we control overall. Resolution is defined as a contribution from one term, square root of n over 4, and we'll define each of these terms so we can think a little bit better about what these terms mean. Because these are terms that we've already discussed in our lectures, and I just want you to see how everything's trying to interrelate with each other. So that's a lot. That's a lot of information. So these three terms influence our resolution. And we've learned a little bit about these. Let's define each of these so we can think a little bit more about them. Square root of n over 4. So the 4 is just a number, but what does n tell us? N, as you recall, is our number of theoretical plates. N reflects efficiency. That's one important factor when we want to encourage resolution. The term that involves alpha, alpha minus 1 divided by alpha. This term involves alpha. So if we look at our equation table that I had, alpha, we defined this earlier. Alpha is known as the relative retention. So this is kind of counterintuitive. It's relative retention factor, or also known as the separation factor. That's another, some of these have two terms to describe them. Separation factor. And we defined alpha earlier as being a ratio of the adjusted retention times for two peaks. Peak 2 comes out later over peak 1. And remember, adjusted retention times, TR2 minus an unretained species divided by TM over TR1 minus an unretained species over TM. Notice TMs cancel out in the denominator. And Let's think about what this is a measurement of. This relative retention or separation factor, it's a measure of the relative difference in the retention of two species. So if it's a measurement of the relative retention of two species, it's a ratio. What do you think it tells us about? It tells us a little bit about selectivity. So this is selectivity. We're red, white, and blue, all American today. This tells us about efficiency. This tells us about the selectivity of how one species wants to be spending time on the column in comparison to another species. The selectivity of the column for one species or another, specifically the stationary phase. That's what's real important here. There's one other factor, K. Let's get a different color pen. We did red, blue. How about green? Green's a good color. K. K is the capacity factor. Everybody see that? K is equal to the capacity factor. Capacity factor. It's also called the retention factor. K, well, this is our value of K for 2. So that's K for sample 2 of species 2. And this is K of species 1. So remember, this is a ratio of our Ks. This is K, the retention. This tells us about how one species is retained in comparison to another. This simply tells us how one particular species is retained. So the capacity factor reflects retention. So those are the 3 features that influence our resolution. Efficiency is in this term. Selectivity is defined by this term. Retention is defined by our final term. And we can control each of these by changing different parameters in our chromatography environment, whether they be changes such as we showed, temperature, flow rate is real important. And when we make these changes, what's really important is the experimental conditions in which we're conducting. Whether we are conducting an experiment using liquid chromatography or gas chromatography. These are going to be 2 factors, two comparisons that we'll be discussing in the last section. But let's just think about, we're going to look at each of these individually. And we're actually going to start backwards. We're going to look at retention first. We're going to look at retention, selectivity, and then we're going to end on efficiency, because we're going to introduce the Van Deemter equation to help us understand a little bit about that. Another equation. So let's think about retention. Our value of K, this is retention. So let's say this is our this is influenced by retention. That's with that factor of resolution. So how do we improve retention when we make changes in our experiment. So retention, changes in our experiment, factors that influence our value, our retention factor, K. So we're going to look at these factors, retention, factors that affect K. How we can make improvements to our resolution by changing factors that influence the retention of a particular solute particle that we're trying to separate from another solute particle. So let's think about changing some parameters. Again, the elution problem that we discussed earlier. Let's look at another chromatogram. I think it's important to look at these to see how we can make changes and encourage separation and resolution, and then how we might make other changes so we get good time for our analysis so we can go home. So let's think of factors that we can change. And again, these factors depend upon the environment where we're conducting our experiment. Gas chromatography. A big factor in gas chromatography that we showed for our original chromatogram is temperature. Temperature, controlling our temperature. Temperature changes. Changes in temperature are important for gas chromatography. Very important. One of the reasons why it's very important is because when we have temperature changes, we change the vapor pressure of the gases that are moving through that environment. If we can lower the temperature, we lower the vapor pressure. That particular component of that gas phase is going to spend more time in the stationary phase, and we can encourage its retention in that particular column. That's in gas chromatography. Liquid chromatography. The changes we make there are going to be in changes in the mobile phase. What we're going to show when we start showing some of the instruments next in this week is that in liquid chromatography, an important factor about the mobile phase is how polar or nonpolar the mobile phase is in comparison to the stationary phase. If we can change the polarity of our mobile phase in comparison to our stationary phases, polarity or non-polarity, we can encourage how long a species will be retained on the stationary phase, because we can encourage it. Does it want to be in the mobile phase or does it not want to be in the mobile phase? Those are the two features that we can change in this case. Remember we showed the general elution problem. Let's go through it again. I have these on today's slides. And we're looking at 4 components. Make things a little easier. Remember, this is time. This is a response. We'll just say absorbance and time again. And we're going to look at 4 species. Again, this is on the PowerPoint, so if you have this, you'll have a better image. So that's an example of a chromatogram. Not the best drawing. Again, look at the one I have on the PowerPoint for today. And we would see that this takes 20 minutes. This takes about 20 minutes. And once again, we get poor resolution between our first 2 and better resolution between number 3 and 4. So changes we can make. one thing we can do for gas chromatography, as I said, we can lower the temperature. And if we lower the temperature, we're going to increase the time that's required for the experiment to occur. And it'll cause retention for our species solid phase, because now at a lower temperature, their vapor pressures are reduced. And in this case, if we reduce the temperature in GC, or if this was a chromatogram that represented a liquid chromatography experiment, and if these species were all polar, okay, what if they're polar and our mobile phase is less polar? Well, that means they're going to spend more time in the stationary phase, and that also would improve their retention. But once again, it's going to take a longer time because those species want to hang on to the stationary phase longer. So we can reduce the temperature in GC, or we can change polarity of our mobile phase in liquid chromatography. So if we do either of those, depending upon what our experiment is, well, guess what? We might improve our separation, our resolution. We might get baseline separation of all 4 of our components, where we start to get a little broadening. Once again, this is going to be at the expense of time. So if this was originally at 20 minutes, this might now take us an hour. The time interval is on your slide for today. I just cannot read it. So there's 1, 2, 3, 4. Okay, good resolution, long time. That's not, depending upon the goal of your strategy, your experiment, you might say, okay, I'm willing to spend that much time. We can make changes incrementally throughout the experiment. And that's one way we can encourage and get the best of both worlds. In chromatography, gas chromatography, we can do what we call program or ramping our temperature programming. So what we do in this experiment, we start at a lower temperature, and then we gradually increase the temperature throughout the experiment. And what it will do is it'll encourage these species that come off sooner to be retained a little bit longer and get our separation. And then these species that come off a little bit later, well, now that the temperature's higher, they can come out of the column a little quicker. And using temperature programming, we can get good resolution of all species in a time that might be better suited for what we want. So for gas chromatography, temperature programming. And we'll be discussing this again in our comparison between gas chromatography and liquid chromatography. Liquid chromatography has another method, another changing of a parameter that's similar to programming our temperature. GC, we slowly increase the temperature throughout the course of the separation. Liquid chromatography, we conduct what we call a gradient elution. Kind of cool. So gradient elution, what that tells us is that this is our original chromatogram, and I'm going to make up some conditions, so hopefully you all understand this. And we're doing the experiment on a nonpolar stationary phase. And these are the guys that come out at the end, and these are going to be the non-polar solute. So what we can do here is we can start a mobile phase that's more polar to get these two guys, or more non-polar to get these two guys off. And then we can slowly change the polarity of our mobile phase so that these come off a little quicker. And once again, we can reduce our time factor for our separation. We'll talk about each of these when we discuss the differences and the similarities between liquid chromatography and gas chromatography. So those are ways we can make changes to our environment to encourage changes in retention. Likewise, we can make changes to encourage selectivity, alpha. Alpha is our selectivity factor. Selectivity. Ways we can make changes here. Once again, this is our selectivity portion of our resolution equation. Selectivity. Depending upon our experiment, if we're conducting GC, we could simply change the column out. Change the column, it has a different stationary phase. So oftentimes changing the complete column might be a choice. For liquid chromatography, a good strategy is to change the pH of the buffers that we're using for our mobile phase. So once again, we can encourage changes to improve our selectivity and once again improve our resolution. So these two factors, selectivity and retention, really depends upon liquid chromatography versus gas chromatography, changing temperature, changing polarity, changing the complete column, changing the pH as we've described. Now we're going to spend some time and talk about how to improve the N factor, our resolution. So this is resolution. Or, I'm sorry, efficiency. It's efficiency. I'm sorry. Duh. Dr. Patton, efficiency. How can we improve efficiency? How can we increase the number of theoretical plates? So let's define N. How are we going to increase N? So N. So resolution. If we want to double our resolution, we would have to increase our number of theoretical plates by a factor of 4 because there's a square root relationship between resolution and the number of theoretical plates. So how do we increase N? Well, remember, N is equal to column length divided by H. H is our HETP. That's our height equivalence of a theoretical plate. To increase N, because increasing N would increase resolution, probably something that you might think would be real easy, just increase the length of your column. Let's increase L. Okay, if we increase the length of our column, we're going to increase the number of theoretical plus what? We also increase our analysis time. Maybe not the best thing. Again, you can do that if time's not a big factor for you, but if time's money, that might not be a good choice just to simply increase your column length to get better efficiency and get a better resolution. So what's your second choice? Well, we can decrease our height equivalence of our theoretical plate. And normally, that's a better choice to make in terms of improving your resolution. Decreasing HETP would increase the number of theoretical plates, which would increase the resolution for the separation process. How we encourage or reduce our plate height, our HETP, is approached using another equation, the Van Deemter equation. So let's introduce the Van Deemter equation to understanding factors that influence our plate height. So this is the Van Deemter equation. It is a fundamentally important. They're all important, but this is a very Van Deemter. The Van Deemter equation defines variables and how we can reduce H, our plate height, height of equivalent theoretical plate. H is influenced by three factors. A plus B over U plus C times U. Okay, A, B, and C. These are all factors that are just constant depending upon the column parameters. Packing material is really important. How efficiently we pack a column. How small the particle diameter is in a column. Some of these values that we're going to list also depend upon the diffusion coefficient of the solute particles that we're trying to separate. The U term is our flow rate, and this is that linear flow rate. U is our linear velocity. Of our mobile phase. So this is the linear flow rate or the velocity of our mobile phase. It's in meters per second or centimeters per second or distance per unit time. So let's define each of these because each of these are related to different features that we can improve in most cases. Let's look at our first term. This term, let's look at A. It's a constant, depends upon certain factors of the column. A is called our multiple path term. Multiple path. In some textbooks or other pieces of literature that you might read, it's also called the eddy diffusion term. Eddy diffusion. Eddy diffusion. Let's think about what eddy diffusion means. I got an image in here. I've heard someone refer to this as the Plinko. It's like playing Plinko. You ever see Plinko? You take a little ball and you drop it at the top of a little slot, and it travels different distances based upon the paths that it has available to it. Again, this is reproduced in your PowerPoint for today. So I'm going to draw an imaginary column. There's our column. There's the exit, and here's the entrance. And in the column, there are particles that make up the stationary phase. So let's use this blue marker. Yeah, that's good. Now the particles have different sizes, so forth, and there's different numbers of them. Some of them are real small. Other ones might be bigger. Some of them have odd shapes, and some of them have somewhat symmetrical shapes. So let's just think of that as our column. We'll put a few more particles in there. Okay, we're going to put our solute in there. We're going to look at individual solute particles moving through that column. This guy moves through, and it finds a really nice path that comes out, and the distance, which would be related to its time based upon our flow rate, will come out in the smallest distance or the smallest time unit if we're looking at a chromatogram. So this one will come out here. Yet another particle that it's in our sample that we put on the very beginning. Again, this is just a sample plug we're putting on the beginning of that column. Another particle, well, he might get lost on the way. Whoa. Notice he's taking a lot of different turns based upon chance. It's like Plinko. He spends a greater time on the column. And then you get that stubborn guy that spends a lot of time. He really gets lost, this last one. So this last one, we'll use green. The last one, well, he starts in here, and he goes down there, and comes up there, and goes down there, comes in through there, goes around there, and around there, and down around there. And he spends a lot of time in the column. Notice all those paths he's taking. He comes out a lot later. So what we end up seeing is that a few particles are like this guy that comes out real quick. They come out through a really nice, efficient path. A couple of them, again, a few of them will take a very tortuous path through that column, and it takes them a longer time. Most of them are going to come out in a fairly average, somewhere around where that red one is. And what we end up with is a profile that has some band spreading due to the different paths that the particles take that make up that band that we're looking at. And so this term, our multiple path term, it doesn't depend upon flow rate because all of them are traveling at the same flow rate. Simply depends upon what path they decide to start meandering off on. They might get lost. What this term does depend upon, it depends upon how efficiently we pack the column as a prepare for chromatography with experience. Another feature that A depends upon, really big important term, is the particle diameter that makes up our stationary phase. And the homogeneity of those particles. Are they all about the same size? If we get a lot of particles that have different sizes, well, that gives us more paths that we can take. If they're all about the same size and they pack real nice, well, that reduces the conduits in which our particles can flow. So these are two important features of our multipath term, not velocity, because the particles that we're trying to separate, it's chance which way they go, not the flow of how fast we're moving. So that's our A term. That's our eddy diffusion multiple path term. So we'll call this multiple path. Let's look at B over U. B over U we call that longitudinal or axial diffusion. And it's inversely related to our flow rate. Now, the term B depends upon two major features. B depends upon, once again, the particles that make up the stationary phase. And the diffusion coefficients of each of the individual particles. So this is a property that's specific for each analyte, depending upon the analyte size and other features. So let's think about what happens and why it's inversely related to our velocity. So let's look at another chromatogram. Or what happens when we put a band. I'm not going to draw any particles this time. I'm simply going to draw a column like we've been doing. There's our column. And what we say happens when we put a sample on there, we put it in there like a plug. I mean, our idea is to go in and just put a sample in quickly. Don't slowly put it in. Just plug that thing in there and bam, it's on its way down the column. So there's our band that we originally put in there. But what happens? Diffusion, longitudinal. Longitudinal means it's diffusion along the length of the column as we travel from the entrance to the exit. Now, diffusion is a two-way process. Regardless of what way the flow of our mobile phase is going, particles in the center where the most concentration is, they're going to diffuse in the forward direction and in the backward direction. And what happens is we get band broadening. So if we look at that one, we get a real sharp peak. A little bit later, the particles start to diffuse backward and forward, but most of them are retained in the center. And we get a slight broadening. And it would be, actually, it would be a little lower. So we would get shortening and broadening. They get short and fat. So what happens at a later time if there's a lot of this diffusion happening? We get a much shorter and broader peak, which isn't good. That's not what we want. So this is our longitudinal or axial diffusion. Now, my question is, why is it inversely related to our flow rate? So let's think about what we can do here. We could speed the flow up. If we speed the flow up, we're going to beat that diffusion because now we're moving that solute down there quicker. There's less time for it to diffuse because we're able to put it up here and then get it out a lot faster. Remember, we said one problem with too fast of a flow rate, and that's our next term, is it doesn't allow retention of the different particles in the stationary phase. And that's our last term that we're going to look at, our C term. So that's our longitudinal diffusion. If we move it fast, this term becomes smaller, and we're not going to get as much of an influence on our plate heights. And that would be good. Fast is good for longitudinal diffusion. If it's slow, if we move that through there slower, it's going to allow diffusion to dominate. The last term that we're going to look at, so this is our axial diffusion or linear diffusion. CU term. See you later. CU is C is our mass transfer term. U is still our velocity. So this term is called mass transfer. So let's think about what mass transfer is. Mass transfer is the transfer of our material from the mobile phase to the stationary phase and back from the stationary phase to the mobile phase. So let's think about what's happening. And again, I have some images here. Let's look at a chromatogram. And we're not going to really look at a chromatic. We're going to look at a flow profile. I think that's a better way to describe it. A flow profile. We're flowing in this direction with our mobile phase. So here's our mobile phase. And down here is our stationary support. It's sitting. It's not moving. And so what we get, we put a sample on there. We put it on as a plug, and it's nice, and it's not too broad. And we get an equilibrium that's occurring between sample in the mobile phase with sample in the stationary phase. Now, what happens as our mobile phase starts to move due to our flow rate? Well, as we move down the column, this peak, this portion that's in the mobile phase moves faster than the portion that's in the stationary phase. It's sort of like lagging behind. So we'll call this time A, and this is time B. So this is still here, and I'm not going to draw it. That it's still there, and it's starting to broaden. I will explain why. And then up here is the movement. Now this is in the mobile phase. And now what has to happen is that this portion that's in the stationary phase is going to try to come back into the mobile phase by equilibrating. And some of this is going to equilibrate back into the stationary phase. And eventually we're going to get equilibrium again. But the problem is, since some of this is slower and it stayed in the stationary phase, later on in time, at time C, we get sort of a smearing outward. We get band broadening. And that's because there's a lag. Some of it retains in the stationary phase. Some of it's moved forward in the mobile phase. And we get this broadening due to this unequivalent transfer of mass between the stationary and mobile phase, because they have different features of how they diffuse and move from one phase into another. Mobile phase is moving faster than the particles that are remaining in the stationary phase. They have to re-equilibrate, and eventually we get a band that's broadened due to this transfer of mass, where some of it's staying in the stationary phase a little longer than some of the guys moving in the mobile phase, which are further downstream. And we get a broader band. Now, this is directly related to our flow velocity, our linear flow rate. Now, let's think why. If we're moving this real fast, well, then we're moving a mobile phase much faster than the equilibration from our stationary phase can meet up with. And that's going to cause band broadening. So that's not good. If we slow this down a bit and allow them to re-equilibrate until we start to move, slowly down the column, then we're going to get better mass transfer, and we're going to not get as broad a peaks. But once again, that offsets our axial diffusion. So what we see in these cases is that there's a fine line that we're balancing. We don't want to move too slow. If we move too slow, we're going to get a lot of axial diffusion. It's going to cause our bands to broaden. If we speed this up, we're going to reduce our axial diffusion. But guess what? It's going to be at the expense of a slower mass transfer from the mobile and stationary phase, once again leading to broad bands. So these are three terms that have a strong relationship, these last two, to how fast we run our samples through a column. So how do we find a happy medium? We have what are called Van Deemter plots. So this is a Van Deemter plot. It helps us to make decisions about what the best conditions, especially for our flow velocities, are going to be, our flow rate. It's a plot of peak plate height, H, versus U, our flow rate, linear flow rate. So let's look at our term A. So let's use purple. So we got a purple there, A. A, like I said before, is independent of what our flow rate is. So we'll just put A here. A doesn't matter. Here's A. A doesn't depend upon flow rate. We'll know what our peak height is based upon how effectively we pack our column, how small our particles are. So let's look at axial diffusion. Let's put this in red. Red term, axial diffusion. So axial diffusion. So at low flow rates, when this is small, axial diffusion dominates, and it gives us a larger plate H value, which is not good. So at low flow rates, this term is big. And it eventually reduces and gets smaller and smaller. So that's our term B over U. When the flow rate's high, axial diffusion is low. And when our flow rate's slow, axial diffusion is maximal, and we get a large plate height. If we speed up our flow rate, our axial diffusion becomes less of an effect, and we get a reduction in our plate height, which is good. Let's look at our last term, our mass transfer term. Mass transfer at low flow rates, nice and slow, we get this transfer of solute from the stationary into the mobile phase, where it's moving slow enough that can catch up and they keep equilibrating. If we start to speed up the mobile phase, well, guess what? Now that's moving too fast, and the stationary phase can't keep up with the equilibration, and it causes band broadening, and that increases our plate height. So what we do is we create a plot that maximizes our flow rate by looking at where these intersect at. And this is our H that we want. That's what our Van Deemter equation tells us, that this minimum in this plot that we have for our blue tells us the best flow rate to conduct our experiment at, based upon all the parameters that we just discussed in this part of our lecture today. So if you're still watching me, I hope you are. That's it for how we control our parameters in terms of resolution. We're going to pick up on our next lecture. Again, I want review questions from people. I'll go over problems, sample problems, but we're going to go in and discuss differences between gas chromatography and liquid chromatography. The first topic we'll start with, I'll review it, is how we can categorize or classify our separation as being either a normal phase or a reverse phase. And I'll just tell you right now, normal phase is when we have a polar stationary phase. Reverse phase is going to be a non-polar stationary phase. And that's how we define it. We'll go over that in more detail next time. Have a good beginning of your week. Thank you.